Hello everyone, this is Wenjun from USSLAB, Zhejiang University. I'm going to introduce our another work, CAPatch, physical adversarial patch against the image captioning system. So, image captioning system is a deep learning based system that aims to generate a text description for an image. For example, given this picture, the generated caption should be a man riding on the back of a white horse. Such a system has been used for intelligent surveillance, blind assistance, image retrieval, and intelligent dialogue. For intelligent surveillance, the image captioning system can help to identify important moments from the huge volumes of videos. It's important to output the correct captions, especially keywords. We proposed CAPatch attacks whereby an attacker can wear a CAPatch to trick the image captioning systems to output benign captions, such that he can bypass the video surveillance system for home security. CAPatch has two types of attack goals. The first one is caption makeover attack, whereby the image caption outputs a completely irrelevant caption. The second is keyword hiding attack, whereby the image captioning system fails to output a decisive keyword describing the image. For example, man. Here's a demo. The man with the CAPatch moved from far to near, and none of the caption contains the word man. You may have a question how to achieve this attack. To achieve this attack, we first analyze the structure of the image captioning system. The image captioning system usually adopts an encoder-decoder architecture. It can be divided to the computer vision side encoder and the natural language processing side decoder. The encoder often uses CNN or faster CNN models to extract the features from the import image. The decoder often uses attention modules and LSTM to generate the output caption with the import features. As the adversarial patches have been proven to be effective against the CNN and faster CNN models in terms of classification and detection, a naive trial is to utilize such a patch to attack the image captioning system. With this idea, we generate an adversarial patch against the CNN-based encoder with the target class bird. With this adversarial patch, the output caption changed from a group of people sitting on a bench and a man in a red jacket to a man sitting on a bench with a bird on the bench. You can see the patch induced the word bird, but the keyword man is still in the caption. This shows the naive adversarial patch can modify the output caption, but it's not enough. Why is it not enough? Because the naive adversarial patch doesn't consider the decoder. To enhance the capability of the adversarial patch, our basic idea is to exploit the vulnerabilities from the system level instead of a single module level. With this basic idea, we carefully analyze the architecture of the image captioning system and then design the CAPatch. As this architecture shows, the image captioning system consists of three key parts: a CNN or faster CNN model for feature extraction, an attention module for image region weighting, and a language LSTM for caption generation. So to generate an effective CAPatch, we design 4 modules, include detection assurance module, attention enhancement module, a caption alteration module, and we also design a robustness improvement module to a real-world attack. Next, we will detailize how we achieve these modules. First, we introduce the detection assurance module. The fast RCN encoder works in 2 stages. In the first stage, its region proposal network outputs thousands of candidate boxes. And in the second stage, its classifier selects salient boxes from the candidate boxes and passes the corresponding feature to the decoder. So we designed the detection assurance module to enable the features of CAPatch to be passed to the decoder. Specifically, we realized the detection assurance module in 3 steps. First, we enhanced the region proposal scores to produce as many boxes as possible over the patch. Next, we enlarged the overlaps between the boxes and the patch. Finally, we improved the classification scores of the boxes to ensure that the corresponding features are salient enough to be passed to the decoder. As a result, we ensure that the decoder detects the patch and passes more features to the decoder as shown in this picture. Then we introduce the attention enhancement module. When generating each word of the output caption, the attention module uses the hidden state vector of STM to match the image features and then generate weights for those features. Then the weighted sum of features is sent to the LSTM to generate the word. So we designed the attention enhancement module to improve the weights of the features that is extracted from the CAPatch. To enhance the attention of CAPatch more efficiently, we first divide the words of the target caption into 2 classes. One is the content words such as bird, sit, and the other is the non-content words such as of, the. Then we select the content words as our target words and render the system to focus on the attention region when generating those words, where the attention region is selected by their intersection area with CAPatch. As shown in this picture, with the attention enhancement module, CAPatch receives more attentions of the image captioning system and achieves better performances. Next, we design caption alteration module to generate the target caption integrally. We estimate the joint probability where we use the words in the target caption to update the LSTM state and multiply the probabilities of the whole sentence. And we calculate CW loss as our caption loss. Moreover, we design a robustness improvement module to ensure the effectiveness of CAPatch in the physical world. We use color smoothing to decrease the impact of the sampling errors and transform the patch for different conditions when training, including resize, rotation, brightness, and contrast adjustment. Eventually, we calculate the final training loss as a weighted sum of the 4 losses. Well, we evaluate CAPatch on 3 representative image captioning systems, including shoe, antenna, and tail, self-critical sequence training, and bottom-up and top-down. We use Microsoft COCO dataset and use 5,000 images for CAPatch training and another 5,000 images for testing. Given the import image size is 600 by 600 pixels, the default patch size is 150 by 150 pixels, which occupies 6% of the image. Overall, we evaluate CAPatch on 6 random target captions. We find CAPatch can always achieve a high attack success rate against various image captioning systems with 2 types of attack goals. There are examples with the target caption. A bird is flying over a body of water, and a cat is sitting on a wooden bench. Next, we evaluate the impact of patch size and angles. From the results, we find the CAPatch can achieve a success rate of over 80% with CAPatch larger than 140 by 140 pixels. We also compare CAPatch with previous attacks and find CAPatch achieved much better performances. Moreover, we evaluate CAPatch in the physical world. We printed a square poster with side length of 30 centimeter and attached it to the volunteer's clothes. We have evaluated the attack effectiveness of CAPatch in different volunteers, different image resolutions, and cameras. From the results, we find CAPatch can work with common resolutions and with 3 representative cameras. We also evaluate the impact of light conditions and distances. We find CAPatch can work in different light conditions and achieve successful attack when occupy only 3% of the whole image. To mitigate CAPatch attacks, we evaluate 5 existing defenses against the adversarial patch. They can be classified into 2 groups, that is, modifying the import images and modifying the model architecture. The results show that those defenses can reduce our attack success rates to some extent, but impair the performance of image capturing heavily. In summary, we propose the CAPatch attack, which can trick the image captioning systems to output a chosen caption or hide keywords. We evaluate CAPatch in both digital and physical worlds, and the physical printed CAPatch can work with various light conditions, distances, cameras, and image resolutions. This is all my presentation. Thanks for listening.
Thanks, speaker.